Welcome guys to my channel. This is Chemistry with Mhin. In today's episode, we will talk about thermochemistry. Thermodynamics, what comes into your mind? Thermo means temperature and dynamics means motion. Thermodynamics is the study of energy changes and the flow of energy from one body to another. What is temperature? Temperature is the measurement of how hot or cold an object is. It is determined by the average kinetic energy of the particles of an object. So we use a thermometer to measure how hot or cold an object is. So when you increase the kinetic energy of the object, you also increase the speed of the molecules. Once the speed is increased, the likelihood of collision in the system will also increase. Therefore, temperature increases, or the temperature is hot. Meanwhile, when you decrease the average kinetic energy of the particle, of the substance, then there will be less collision in the system since there will be a decrease in the movement of the molecules. Therefore, a colder temperature. There are three types of system interaction: isolated, closed, and open. Isolated system has no exchange of matter and no exchange of heat. One such example is a thermos. As you can observe, if you put hot water on a thermos, the heat will not escape. Therefore, it's a good container for retaining hot objects. Meanwhile, closed system cannot exchange matter but can exchange heat energy. One such example is a jar with a lid on. It can exchange heat energy but it cannot exchange of matter. And lastly, open system. It can exchange both matter and heat energy. So one such example of an open system is a glass of water. What is heat? Heat is the transfer of kinetic energy from one medium to another. So there are three ways to transfer energy or heat, which is conduction, convection, and radiation. Conduction is the transfer of heat from one substance to another by direct contact. One such example is heating the metal pan into the fire. Convection is the transfer of heat through a liquid or gas caused by molecular motion. One such example is a hot air balloon. Radiation is the energy that is radiated or transmitted in the form of X-rays or waves or particles. One such example of radiation is the UVC light emitted by the sun. There are four laws in thermodynamics. The zeroth law, also known as the equilibrium principle. The first law is the energy principle. And the second law, the entropy principle. And lastly, the third law, which is the temperature principle. In the zeroth law states that if object A is in thermal equilibrium with object B, and if object A is in thermal equilibrium with a third object C, then object B must be in equilibrium with object C. The first law of thermodynamics states that energy cannot be created nor be destroyed, but it can be converted from one form to another form. Diet and exercise is a very effective way to shed off unwanted fats. According to the first law of thermodynamics, food is our main source of energy. If you take in more energy than what you use during the day, your body stores them as fats. However, if you take in less energy than what you needed, your body uses these reserves to keep you going. If your intake is just equal to your energy requirement, then you will maintain your weight.
The transfer of energy is either exothermic or endothermic process. Endothermic process describes a process or reaction that absorbs energy from the system to its surroundings.
One of the characteristics of endothermic reaction is that the product is bigger than the reactant. Example of endothermic reactions: making of ice, cooking a raw egg, and photosynthesis.
The term exothermic process describes a process or reaction that releases energy to the system to its surroundings. One characteristic of exothermic reaction is that the reactant is larger than the product. Example of exothermic reaction: the heat of the sun, burning of wood, and corrosion of metal.
The first law may be written as U plus Q plus W, where U is the internal energy, W is the work, and Q is heat.
Q is positive if heat is added to the system. Q is negative if heat is released to the system. W is positive if work is done on the system. W is negative if work is done by the system.
Let us try to solve some problems. Alright, what is the change in internal energy of a system that absorbs 500 joules of heat and does 300 joules of work? So, let's determine the given. So, heat, or Q, is 500 joules. Work is negative 300 joules. Why? Because it does work on the system. If it does work on the system, then it's negative. But if done by the system, then it's positive. Alright. Why heat is positive? Because it absorbs heat. But if it releases heat, then it's negative. Now, let us set up the equation. So, we want to look for the internal energy. So, U is equals to Q plus W. Now, let's input all the values. So, U is equals to 500 plus negative 300. Okay, it's joules and joules. So, U is 200. That's the final answer. Let's try another example. How much work is done on the system that has internal energy change of 100 joules and heat release 80 joules? So, let's look for the given. So, the given is, there we go, the given, we have U, or the internal energy, 100 joules, Q, or the heat is released. We know that it's 80, however, the heat is released, so it's gonna be negative 80 joules, and what's missing is work. So guys, what will be our equation? So the initial equation was U is equals to Q plus W. However, we just want to have this. So let's transpose Q to the other side. So U minus Q equals W. So what's the value for internal energy in the given? 100 joules. What's the value of Q? Negative 80 joules. and W there. So 100 minus negative 80, that would be WE work is 180 joules. That would be our final answer. Enthalpy is the amount of heat absorbed or expelled by the system to cause a change in the system.
Enthalpy change can be determined using the actual enthalpy of formation of each of the substance present in the thermochemical reaction. Enthalpy of formation is the enthalpy associated with the reaction that forms 1 mole of a compound from its element in their most thermodynamically stable states. These are measured on a relatively scale, and for elements, the enthalpy of formation is equal to 0. The standard enthalpy of formation is the enthalpy change when 1 mole of the compound is formed from the elements in the stable place at 25 Celsius at 1 atmosphere. The standard enthalpy formation can be used to determine the standard enthalpy of reaction. Enthalpy of reaction is equal to the sum of enthalpies of the product minus the sum of the enthalpies of the reactants.
We want to calculate the enthalpy of the following equation. So we need to use this equation to solve the enthalpy. This equation right here. So which is the product? This one or this one? So if your answer is this, then you're correct. So let us set up the equation. So 3C plus E, don't forget the parentheses, so you won't forget about it. So A, then the reactant, so A plus 2B. So next step, you just need to substitute the values in the table. So what's the value for C? 300. What's the value for D? 400. What's for the value for A? 100. And what's the value for B? 200. So let's add everything. 900 plus 400 minus 100. So this is the final answer. So is this exothermic or endothermic? So which is it? If product is bigger than reactant, then endothermic. H is positive, then it is endothermic. If reactant is bigger than product, then it is exothermic. Let us do another problem. Calculate the enthalpy of the combustion of the acetylene. So, we have this equation. In order to solve this, you must use this equation. Now, which of this is the product and which of this is the reactant? So, if your answer is this, you're correct. This is the product. Meanwhile, this is the reactant. Now, let us set up the equation. So, for CO2 plus 2 H2O there minus 2 acetylene C2H2 here plus 5 times oxygen. Don't forget to put parentheses so you won't get confused later on. Alright, now that we have set up the equation, we need to substitute the values from this table. This is the standard enthalpy formation. So let's substitute. So what's the value of carbon dioxide? It's negative 393.5. Then, what's the value of 2H2O? 2 negative 241.8 minus, what's the value of acetylene? It's 206.7. What's the value of oxygen? It's 0. Now, let's add and multiply everything in this equation. So what's the value? In this one, 4 times negative 393.5, it's equal to 1,574 plus 2 times 241.8, that's 483.6, parenthesis, minus 2 times 226.7, that's 453.4 plus 5 times 0, 0. So, add everything. 1,574 plus 483.6 minus 453.4, that's 1,604.2 kilojoules per mole over mole. Here you go. That's the answer. So, is this an exothermic or endothermic process? So, if the equation is positive, then if H is positive, then it is endothermic.
Hess' law of heat summation states that for a chemical equation that can be written as the sum of two or more steps, the enthalpy changes for the overall equation is the sum of the enthalpy changes for the individual steps.
Okay, let's have some examples for Hess law. Calculate the enthalpy of the reaction of this equation from the following data. So we want this equation, we want to find out the enthalpy of this equation. So we're going to use this. Just like algebra, we have to cancel out the unnecessary terms. So let's leave this as it is. Then we have to transpose this to the other side. So a plus b to x plus 4y, x plus 2y, and c plus 2d. There you go. So can you already remove this? No, you have to make it equal. So in order to make it equal, you have to multiply it into 2. So this will become 2, this will become 4, this will become 2, and this will become 4. So it's going to be cancelled. There we go. So what we are remained is 4a, ab plus b, current, this, and then since we multiply it by 2, we have to multiply the enthalpy also by 2. And then we also reverse this, so it's going to be negative. So H is 50 and H is negative 200. So this is H to the negative 150 kilojoule per mole. Kilojoule per mole. Okay. Now that we got this, that's the final answer. We want to calculate the enthalpy of the reaction of this equation, but we only have this following data. So we're going to use Hess' law to solve this problem. So we want this to stay. So we have this. We want this to stay. And we want this to stay. So let's look at it. So this one, as you can see in this equation, we want this and this to be intact. So this is going to be the same. Meanwhile, we want this to go to the other side, so we have to transverse the equation. So let's transverse this. So this will become 202 CO2 plus 3H2O, arrow sign 6 to H6 plus 3 1 half oxygen. Now, what will happen to the H since we reverse them? So it will become 1560 kilojoules. Now that we have that, we have to get rid of the unnecessary elements. So we want to delete this. So it's going to be deleted since here it's going to be deleted too. This one is going to be deleted. This one, this one, this one, and this one. And this one, and this one. So what we're left was, oh yeah, I haven't forgot to delete this one. So we remain this. H24 plus H2 from here, and C2H6. Now what about this? Now, okay, let's cancel this. So all we need to do is add all of them. So the final answer is negative 137 kilojoules. And that is our final answer. Let's try.
The second law of thermodynamics states that entropy is a measurement of the disorder in a system. All system gains entropy over time. The second law of thermodynamics says that the total entropy of both a system and its surrounding will never decrease. Let us discuss order and disorder. It is very easy to create disorder out of order. For example, it is easy to mess up your life than to fix it.
Clausius states that heat flows naturally from hot to cold object, but it doesn't mean that it is impossible for heat to flow from cold to hot body. But it doesn't happen naturally or spontaneously.
Entropy of the universe is the sum of the entropy changes in the system and in the surrounding. This is used to determine whether the process is spontaneous or not. So, if S universe is positive, then it is spontaneous. And if it's negative, then it's non-spontaneous. Entropy of the system is the difference in the standard entropies between the product and the reactant. Entropy change of the surrounding is due to the flow of heat and therefore depends on the enthalpy of the system. Entropy of the surrounding is also inversely proportional to the temperature.
Okay guys, let's have some more examples. So calculate the entropy changes in the S system, S surroundings, and S universe for the following reaction at 25 degrees Celsius. So in order to get the S universe, you need to have S surrounding and S system. To get the S system, you must use this equation, this one. Okay. So let's try to solve this. Okay. Let's try to solve this. So we have the values here. So we're going to use this value, the entropy values, in order to get the S system. So first, which one? Let's set up the equation. Which one is the product? This one or this one? So if your answer is this, then you're correct. Okay. Now let's set up the equation. Okay. Here we go. So parenthesis 4 CO2 plus 2 H2O parenthesis, another parenthesis, minus the reactant, which is 2H2H here, and then plus, this plus 502. Alright, now that we have this, let's substitute the values. So 4, here's the value of CO2, 213, 213.6 plus 2 times 188.7 minus the value of C2H2 acetylene 224 and lastly plus 205. Oh yeah, don't forget the coefficient here. Times 2 times 5. Now, get the answer here. So let's get the calculator and then let's solve this. Alright. The 4 times 213.6. That's 800. Wait. Okay, that's 854.4 plus 2 times 188.7. That's 377.4 minus 2 times 224 parenthesis 448 plus 5 times 205. That's 1025. There we go, 1025. Now that we have this, let's add and subtract everything. 854.4 plus 377.4. That's 1231.8 minus 448 plus 1025 minus 1473. So minus 1239.8. So the answer will be negative 241.2. So S round. That's the S round. Now that we have the S round, let's get the S round. Let's get the S. Oh, sorry. We got the S system. Now we're gonna get the S round. Sorry, this is the system. Here we go. System. Now let's save this for later. So let's put it here. S system is negative 2412. Now let's delete this so we can get the S surrounding. Alright. How to get the S surround? So we're gonna use this equation. So this is enthalpy over temperature. So let's look for the enthalpy. Same as this, but instead of this, we're gonna use this, the enthalpy. So let's calculate again. So 402 plus 2H2O minus 2C2H2 plus 502. Now, let's substitute the values. So, negative 3.5 plus, oh, don't forget to multiply the coefficient. This is 4 right here. Let's erase it so it would be a lot clearer. So, here. 4 times negative 393.5 plus 2 times negative 241.8 okay, parenthesis, minus 2 times 22.7 plus 0 times 5. So let's add everything. So parenthesis 4 times negative 393.5 parenthesis plus 2 times 241.8 parenthesis subtract by 2 times 227. So the total would be H is equal to H 1603.6. So the reaction is in 25 Celsius. So let's convert that to Kelvin. So that's 298. So S around is equal to negative 1603.6 divided by 290. Okay, so now that we have the answer, so the final answer would be S around is equals to 5.38. So final answer. Okay, now that we have S around and S system right here, let's add them. So according to the system, S universe is equal to negative 421.2 plus 5.38 plus negative 241.2. That's S universe is negative 235.82 kilojoules per mole. That would be our final answer. Gibbs free energy is a thermodynamic potential that can be used to calculate the maximum of reverse work that may be performed by a thermodynamic system at a constant temperature and pressure. There are two ways in calculating the Gibbs free energy. First, by determining enthalpy and entropy, or using the tabulated values of free energy of formation of Gibbs free energy. If both enthalpy and entropy is negative, then it is spontaneous at low temperature. If both entropy and enthalpy is positive, then it is spontaneous at high temperature. If entropy is positive and enthalpy is negative, it is non-spontaneous at all temperature. If both entropy and enthalpy is positive, then it is spontaneous at high temperature. If entropy is positive and enthalpy is negative, it is non-spontaneous at all temperature. Let's try to solve more problems. Calculate the Gibbs free energy change for the following chemical reaction. So, let's determine the given. We are given a temperature of 293, given 293 K or Kelvin, that's temperature. We are also given the enthalpy, which is 19,070 H, 19,070, and the entropy of 90 calories. So, we're going to use this equation to solve the Gibbs free energy change. Now that we have the equation, let's input the value. So, G is equals to 19,770 minus 273 Kelvin times 90. Now let's solve the equation. So let's see what's the answer. So 19,070 minus 90 times 273. So the final answer is negative. So the final answer is negative 5,500. So now that we have the Gibbs free energy, let's determine if the equation is spontaneous or not. So, since this is negative, so it's non-spontaneous. So if it is negative, then it is non-spontaneous. Let us try to solve another problem. So, the problem is, at a constant temperature, find the Gibbs free energy of this equation. So we have this equation right here. Let's see. Right here. Right here. Alright. So first step, let's determine which one is the product and which one is the reactant. So this is the reactant right here. And this one is the product right here. So why are we going to use this equation, since this is ideal if this equation is ideal if the temperature is constant. So use this if the temperature is constant. So let's set up the equation now that we know what's the reactant and the product. Alright. So product, reactant. Right. So 2 NO2 minus 2 NO N2O4. So now that we have this, let's substitute the value from the table. So 2 times 51.3 kilojoule per mole minus 2 times 99.8 kilojoule per mole. Now let's multiply it. So 2 times 51.3, so the answer is 102.6 kilojoules per mole minus 2 times 99.8, that's 199.6. So let's subtract it. 102.6. So that's 97 kilojoules per mole, negative to be exact. Negative 97 kilojoules per mole. So if G is positive, then it is spontaneous. And if G is negative, then it is non-spontaneous. So now that we know it's negative, it is non-spontaneous.
As you might suspect, the Gibbs free energy change is closely related to equilibrium constant, which you have already encountered as a measure of the favored direction of the reaction. Large value of the equilibrium or positive corresponds mostly product favored or favors forward reaction, and small values of equilibrium or negative indicates mostly reactants or favors reverse reaction. The relationship of these two quantities is shown in the equation below, where Gibbs free energy is equals to negative rate times temperature times equilibrium constant.
Calculate the Gibbs free energy of the reaction below at 25 Celsius. So we have this equation. So first let's determine what's given. So we are given the standard equilibrium, which is 3.2 raised to the negative 34. Then rate is constant, which is 8.31 joules over mole. Temperature, which is Kelvin, which is 25 degrees. Now we have to convert it into Kelvin. That's 298. So what is missing is the Gibbs free energy. This is ideal to use when you have the equilibrium constant. So let's start solving the problem. Now that we know the equation to use, all we need to do is G equals negative RT ln K, rhythmic logarithm. So G is equals to 8.31 joules per kilomole times 298 Kelvin, and then L and ln, what's that? So ln Ln is equivalent to 3.2 times to the negative to the power. So use your calculator. 1.9 raised to the fifth. So cancel. So what's remaining was kilomole, joules per mole, joules over mole. So that would be the final answer. Find the equilibrium in the reaction below. So this is our equation. So we're missing the equilibrium constant, but we are given the Gibbs free energy, and we're gonna assume the temperature to be 298. So let's set up the equation. So given G is 223,000 joules over mole, rate is always 8.3 joules over kilomole, and temperature, let's assume it's 298, which is the standard, 298 Kelvin. So let's set up the equation. Since the one is missing is this, so let's do this. So the equation will be this, because we just want the equilibrium constant alone, the right side. So let's substitute the values. So 23,000 joules per mole over mole, 8.31 and 2.98 Ln K. So we have Ln K equals negative 8.60. So we want to remove this. So to remove that, we have to do the exponents. So the cancelled. So this will be cancelled. So K is equals to 1.08 times to the fourth. That would be our final answer.
In reverse process, the system changed in such a way that the system and the surrounding can be put back in their original states by exactly reversing the process.
One such example of reversible process is melting of a popsicle. You can still reverse it back to its original structure by freezing it.
Irreversible process cannot be undone by exactly reversing the change to the system. All spontaneous processes are irreversible. So one example is when you cook a raw egg, you cannot change the cooked egg into a raw egg.
The third law of thermodynamics states that the entropy of a perfect crystal is zero when the temperature of the crystal is equal to absolute zero. As you decrease the temperature, there is a decrease in kinetic energy. But once it is in this absolute zero, the kinetic energy is also zero. Specific heat is the amount of energy needed to raise the temperature of 1 kilogram of a material by 1 Celsius. The formula for specific heat, just remember Q equals mcat, where Q is the energy transferred, m is the mass of the object, C is for the specific heat capacity, delta T is the temperature change.
Has the highest specific heat capacity? Is it A, plastic, B, water, or C, gold? So if you answered water, then you are correct.
The human body is composed of 70% water. So what will happen if water has a low specific heat?
The main function of water in the human body is to regulate the temperature. So, if water has low specific heat, water will quickly increase the temperature in the system, thus disrupting the normal homeostasis of the human body. So, for example, denaturing the proteins in the body as the temperature increases.
Let us try to solve more problems, okay? The temperature of copper with a mass of 60 grams changes from 25 to 30 Celsius. When the metal absorbs 200 joules of heat, what is the specific heat of the copper? So, let's determine the given, the equation what we're gonna use, and the final answer. So let's try it right now. So what is the given in this problem? So what is given? So we are given the mass. We're also given the initial and final temperature. So the given is given. Mass is 60. Final temperature is 30 degrees. Initial temperature is 25 degrees. And Q is, or heat, is 200 Celsius. So Q equals M cap. So we're missing this, the specific heat. So we want the specific heat to be alone in this side while transferring M and T. So let's divide M, change of temperature, to this equation. Now, let's substitute the given. So 200 joules. So 30 minus 25 for us for the temperature, and 60 grams. So 300 over 200 joules. Like this. So the answer would be 1.5 joules over grams times Celsius. So this is the final answer. Okay, given 50 grams of sand where the specific heat is 0.85 at an initial temperature of 30 degrees, what is the final temperature of the substance when it's absorbed 4 joules of heat? So, our given is 50 grams, that's our mass. Specific heat 0.85. Initial temperature is 30. The final temperature missing, and heat is 4 grams. So our equation is Q equals M cap. So let's arrange this. So Q MC cap MC. So what's remaining is T, and T stands for initial minus temperature minus initial. Q is MC TF, temperature final, and temperature initial. So we just want this on this side and this one on the other side. So QMC over C minus, okay, plus initial temperature equals TF. So let's substitute. Now that we have our equation, let's substitute the value. So 4 joules, 0.8 times 50 plus 30. So let's calculate it. So the answer is 0.1 plus 30 equals 30.01 is the final temperature. Calorimeter, it is a means to measure heat transfer during chemical or physical process. There are two types of calorimeter, bomb calorimeter and coffee cup calorimeter. A coffee cup calorimeter, or aka styrofoam cup, to provide insulation when materials are mixed inside of it. A styrofoam cover and a sensitive thermometer complete the apparatus. Coffee cup calorimeter maintains constant pressure but volume changes may occur. Bomb calorimeter is used to determine the heat of combustion of a chemical reaction. It maintains the constant volume during the process. Okay, let's try some more problems. So, a 25-gram sample of metal is heated to 300 degrees and it's placed into 500 grams of water. At 20 Celsius, if the final temperature of the water is 50 Celsius, then what is the specific heat of the metal? Alright, so first let's find the given. So we're given metal, water. So mass of metal is 25, mass of water 500 grams. Initial temperature 300 Celsius. Initial temperature of water is 20 Celsius. Final temperature, it's 50 Celsius, another 50 Celsius for both water and metal. Specific heat is missing for metal, and water, the specific heat of water is 4.18. So let's set up the equation. So we know that Q loss is equals to Q gain. So remember the second law of thermodynamics, that heat flows to hot to cold. So which one is hotter, the metal or the water? If your answer is the metal, you're correct. The metal will lose heat while the water will gain heat. So let us set up the equation. So M cat for metal and M cat for water. Now that we have set it up, we have to make sure that the specific heat of metal will stay here while transposing the mass and the temperature of the metal to the other side. So in order to do that, you have to divide mass and temperature. So let's do this. Here, MC cat over MC P. Now that we have our final equation, let's substitute the values. So C is equals to 20. This is water. So what's the mass of the water? 500 grams. What's the specific heat of water? 4.18. What's the final temperature? 300. Oh, sorry. 50 is the final temperature, and the initial temperature is 20. Now that we have that, what's the mass of the metal? That's 25. And the change of temperature, so the final is 50 and the initial is 300. So let's solve this. So 500, so 500 times 4.18, that's times parenthesis 50 minus 20. So we got 62,700. Now, let's solve the denominator, or the mass of metal. 50 times 250, that's 12,500. So let's solve this. So 62700, 62,700 divided by 12,500. So the specific heat is 5.0.116. That is our final answer. So let's try some more examples. How much will the temperature of a cup of coffee at 100 degrees Celsius be reduced when a 50-gram silver spoon with a specific heat of 0.25 at 25 Celsius is placed in the coffee and the two are allowed to reach the same temperature? Let's assume the coffee has the same density and specific heat as water. So, let's set up the equation. So, mass of coffee is 200 grams. Initial temperature of coffee, 100 Celsius. Specific heat, it's 4.18. Why? We have to assume that the specific heat of water in coffee is just the same. So we're missing final temperature. So let's move on to the silver spoon. So the mass of silver spoon is 50 grams. Initial temperature is 25 Celsius. And the specific heat is 25 Celsius. 0.25. And then final temperature is missing. So let us set up the equation. So Q loss equals Q gain. So MCAT So which one is lost? Coffee or the silver spoon? So the coffee will lose temperature, while the silver spoon will gain some temperature. So let's try to answer it. So the coffee is 200 times 4.18. So what's the final? Final is missing. Initial temperature is 100. So equals to 50 minus 0.25. TF is still missing. And the initial temperature is 25 degrees. So let's try to answer it. So 200 times 4.18, that's 836. So you have to distribute this. So TF minus 836 83,600 is equals to 50 times 0.25, that's 12.5 TF minus 25, 312.5. So let's move all the TF in the left side, and then let's move the non-variables to the right side. So 306 TF plus 112.5, so 83.60 minus 3.215. So let's answer it. So 836 plus 12.5, so 848.5 TF, and then 83,600 minus 312.5, that's 83,287.5. So let's divide. TF is 848.5. So let's divide it. 4.5. So the final temperature is 98.5. That's our final answer. Here's another problem. A student made an experiment to determine the enthalpy of the combustion of glucose in 500 grams of water at an initial temperature of 25 degrees. As the combustion occurs, the temperature raised to 30 Celsius. What would be the heat of combustion for the reaction? The heat capacity of the calorimeter is 3 kilojoules over Celsius. So let's determine the given. So we are given mass of water 500 grams, then initial temperature Ti 25 Celsius, final temperature is 30, heat capacity of calorimeter is 3.00 kilojoules over C. So let us set up the equation. So Q RXN minus specific heat of bomb calorimeter plus specific heat plus mass of water plus specific heat of water times change in temperature. So let's set up this system. So what is the heat capacity of the calorimeter? It's 3 kilojoules over mole plus, what's the mass of water? Oh, sorry, this is multiplication. Alright. Well, what's the mass of water? 500 grams times the specific heat of water, which is 4.14 raised to the negative 3 kilojoules per GC times 30 minus 25. So let's do everything. So 3 plus parenthesis 500 times 4.18 raised to the negative raised to the negative 3 times 5. So the answer will be Rxn minus 20. That's the heat of the reaction. That would be the final answer. Don't forget to hit like and subscribe for more content. Bye guys, and see you soon for more chemistry with Mhin.